is Thomas Hertog. So Thomas, if you would like, you can go ahead and share your slides while I introduce you. So he is the professor at the Institute for Theoretical Physics at University of Leuven in Belgium. And he's working in LISA Fundamental Physics Working Group. So as just to remind the audience, we have again, the suggestion is 20 minutes talk and 10 minutes discussion and questions. Please go ahead, Thomas. I think you're muted. I can unmute you. Yes.
Yes, good, thanks. Yes, so good morning or good afternoon, everyone. It's a pleasure to give a brief overview of the Fundamental Physics Working Group at LISA. And so this is chaired by these three gentlemen: Philipp Jetzer at Zurich, Nicolas Younes at Illinois, and then myself. You can email us on that email address. But of course, I guess this has been explained before. To become a member of these working groups, you have to become a member of the LISA Consortium, at least an associate member of the consortium, right? That's the way it works. Good. So as everyone knows, this is the LISA mission. This is my favorite plot of the whole thing. The blue thing is what we hope to see when the instrument flies, and then buried underneath is all this super exciting, interesting fundamental physics from all sorts of different corners of our expertise. And so it's a huge challenge to dig this up. To do that, there's this giant consortium that hopes to achieve all this. And just to orient you, we are down. I don't know if you see my mouse, but we are down here at the bottom of the organigram. There are two important points about our, so to speak, location in the LISA consortium. We straddle the bridge really between the broader LISA science, or you could say, yeah, gravitational wave science or gravity science community, and the consortium activities. So that means that the Fundamental Physics Working Group is not strictly bind to the LISA deliverables, but its aim really is to connect the LISA science to the broader interesting ideas in the community. We report or interact, I should say, mainly with the LSG. The LSG is the LISA Science Group. That's what you see on the bottom right here, which combines the key science objectives, deliverables of all nature that the consortium has signed up to. And there is one, of course, there's one item among these. It's called interpretation here. I've lost my mouse now. It's called interpretation here. And this is especially where the fundamental physics input goes. So if right, and so these, this is taken out of the table of contents of the LISA Science Group. That's all about this interpretation item. And so you see a whole range of different topics here, which range from mainly astrophysical oriented studies to as pure fundamental physics as it gets, like testing the nature of black holes or general relativity. Many of these topics, of course, don't fit either into the branch of fundamental physics or cosmology or astrophysics. In fact, when it comes to gravitational wave observations, many of these topics really intertwine these different branches. So in a sense, if you go back to the consortium overview, you have the different working groups here: the cosmology group, the fundamental physics group, the astrophysics group, the data channels, but there's a waveform group somewhere. So all these different science strands really, one way or another, have to come together. So concretely, what is our mission at the Fundamental Physics Group? Well, very broadly formulated, we want to foster work and collaboration on all areas of fundamental physics that are relevant to LISA. Or vice versa, we want to exploit LISA, or to make sure or to help exploiting LISA's science potential to the full extent possible. As I mentioned, this is really meant, this working group is really meant as a liaison between the key consortium deliverables and the broader gravity community. We want to keep it that way for a number of years. We are early still in the mission, and there's a lot that can happen. And it's very important that by the time the instrument flies, we are firmly and solidly embedded in that broader gravity community. Yes, well, of course, there's a broad range of topics. I'll come to that. There are all sorts of interconnections with the other working groups. I've mentioned that. And the bottom line really is to strengthen the LISA science case. There are about 350, 400 members right now. There's a rotation of the chairs coming up. And I'm going to give you a short flavor of a few of our activities and what's coming up. It all started around the end of 2018, where we had our first meeting at Florence at the Galileo Galilei Institute. And out of that meeting, it really came a sort of what you could call a manifesto for the working group, which was at the time very much science-based, by which I mean this was a first reflection on what are the different directions or areas in fundamental physics where LISA could provide input, which could be relevant for LISA. So this was not so much at the time we were worried about feasibility or measurability or observability. We were really interested in how can we really connect cutting edge fundamental physics to LISA. And this is sort of an overview of that paper that came out of the workshop, where you see various arrows emerging from fundamental physics, ranging from more cosmologically oriented fundamental physics questions like the nature of dark energy or the nature of dark matter, to pure gravity or traditionally pure gravity topics like the nature of black holes, the dispersion, symmetries, equivalent principles, tests of equivalence principle, and so forth. Of course, there's the most mysterious arrow going to the left, which says other model-independent tests. Yeah, as we all hope, it's a whole zoo of corrections and models that go beyond relativity, general relativity, and who knows, maybe something shows up. Even at that first workshop already, it became abundantly clear that the link between fundamental physics and LISA is going to be intertwined enormously with astrophysical and waveform systematics. So we're building on that right now. In fact, on that early paper and these early discussions, we're in the process, like all working groups of LISA, of writing a white paper, which gives a more coherent roadmap to move forward to move forward, in other words, from more pure science-based considerations and directions towards an implementation, or at least towards giving a roadmap to implement some of these into work packages and concrete objectives for the mission. Our white paper is, yeah, as I just mentioned, really conceived as a research roadmap and not so much as another review articles, because we feel there have been a few excellent recent review articles already. So it's meant, in other words, very much as a living document. Yeah, so this is the timeline, but this is perhaps less relevant for now. Okay, yeah, so this is the content of the white paper. Yeah, so these are the same 8 arrows that left from the manifesto, right? And so that we are developing further in this white paper. Here is just one example of one science example of what I meant when I say that there are interconnections between all these different working groups and science objectives. On the right here, you see the typical plots of quasi-normal mode frequencies. The top layer are frequencies for the first mode, frequencies for the Kerr geometry, and then the other graphs represent corrections to these in 2 particular corrections, or no, how should I say this? 2 particular, yes, corrections to modified theories of gravity, which are reasonable corrections to general relativity. The different color codes here represent the spin of the black hole. Chi is the spin of the black hole. So that's a typical fundamental physics kind of input at a very pure science-based level. You apply theoretical considerations to constrain meaningfully corrections to GR, and you translate these into frequencies or corrections to frequencies that play out in the ring down phase of the signal. Now, those very same theories, of course, if they are there, if they exist, if our universe obeys those, will manifest themselves on very different scales, also on cosmological scales. And so then you go to the left, to the left of the screen, and there you see these very same corrections to GR manifested in a modification of the inflationary spectrum of fluctuations. And so the whole field is full of those connections between, and now I'm not even including astrophysical considerations, which you would need to do when you were about, or when you want to measure these quasi-normal frequencies on the right. So this whole, I think I see the future of these working groups and of this field in general, really as strengthening the connections between fundamental physics, cosmology, and astrophysics. In fact, I think there's a huge opportunity for LISA to become a flagship mission in that respect. Okay, wait a minute. Yes, okay, good. Yeah, so I conclude with a few remarks. The way we operate for now, we have been operating as what is called in the LISA Consortium an open forum, meaning that discussions, collaborations, initiatives are open-ended in the sense of they're not tied to specific deliverables or objectives of the LISA mission. That's also the reason why one can be an associate member of the consortium, and one doesn't need to be a full member in order to join the working group. Of course, this is also, of course, in line with the stage of the mission. Many of these key science objectives and so that work package of the LSG that I've mentioned are, yeah, of course, at this moment in time, not top priority. They're really, we should be ready in 2030. So we should keep and maintain and nurture that open forum channel, I think. That said, it's clear that we're going to be starting to think about the next stage and in particular strengthen that transition to the actual work packages of the LSG. That's a whole transformation for fundamental physics field, which is not used to work in larger collaborations or yeah, even just with concrete deliverables and work packages. So it's going to be, we're going to need a bit of a change of culture to some extent, I think. But it's clear there's an opportunity there.
Sorry, Thomas, you have.
And as I mentioned, there's a huge science potential in the cross correlation, in the cross fertilization really between these work packages. And then just to conclude, you're all welcome for our next workshop, January 2022. We had to choose Brussels as a location because after this pandemic, everyone really needed a beer. Thank you.
Thank you very much for the nice talk and the information. Let's thank our speaker, again, virtually, of course. There are questions here. Actually, I have a question myself, but let's first go with the question from the audience. So the question is that what is the best way to get involved with the FP, this fundamental physics working group, in particular for physicists in Canada? I think you're on mute. You're muted.
Sorry. Yes. Yeah. Logistically, it's very easy. Of course, you become an associate member. Now, membership itself is through your national contact point, typically. Then, science-wise, as always, right? Through come to our workshops or join some collaboration. There is no, the barrier to become involved is very, very low. The working group, in some sense, is a way for people to enter the LISA community and to sort of look around and explore before committing to one or another objective, which would involve which would imply an involvement at the level of the LSG, the LISA Science Group. Sorry.
Okay. Yes, thank you. So we have further questions before going there. Maybe I myself ask a less logistic question. So is there any feasibility of LISA being able to observe quantum gravitational effects in black holes or maybe beyond the scattering surface, something like that?
Well, it's not excluded, as you probably know. It all depends. There's a huge uncertainty about what is the scale at which quantum gravity effects set in. The opinions range from it's the horizon scale of a black hole, or it's much, much smaller, or you need an extremely old black hole. So in a sense, that is an interesting situation, right? We don't really know. And so that's where LISA comes in. Where would you look? It is quite clear, I think, that it's either the quasi-normal modes of the loudest events, or it's the EMRI, it's the golden EMRIs. We can expect a few EMRIs within the lifetime of the consortium, of the mission. If there is a good one, that is a very stringent test, provided we get all the astrophysics and the waveform systematic sorted out.
Yeah, that's quite exciting. So let's see what will come out of the experiments. So there is another question. Can you give an example of what sort of work package the fundamental physics working group might produce? Would these be specific searches or analyses?
Yes, absolutely. The transition between, so I've mentioned a few ideas, like studies of quasi-normal modes or MRIs in the presence of dark matter, for instance, variability of the cosmological constant. There's lots of ideas. The question, of course, is which ones are theoretically sufficiently well developed and sufficiently well grounded and feasible to translate into a key, into an objective, into a key work package. Because of course, LISA has key deliverables. It is not easy. It's not trivial. It's not trivial to translate this into an actual work package. And so we will. This is the next stage. That's the stage that I mentioned at the end of my overview. I want to begin to explore how we really make that transition.
Okay, thank you. There is another question. What is the boundary between fundamental physics and other working groups such as cosmology or astrophysics in terms of topics?
Well, I can give you my personal opinion here. I think it might have been clear from what I was saying. I think the boundary is greatly exaggerated. In fact, my opinion is that the boundary is artificial. Of course, you need some organization in the consortium and in between working groups and this and that. But I think maintaining too much of a stringent boundary will, in a few years, hinder the science.
And another question
it's a bit like what was happening in particle physics. You see, in particle physics 20 years ago, people started to do particle physics in two ways. At accelerators and colliders and out there in the universe. If you look at the horizon of gravitational wave physics, we're going to be making the same transition. Black holes are our particles and the universe is out there. We're going to have to connect these two to get the science out.
Excellent. Yeah, exactly. So it related to that question. Another maybe logistical question is that, is membership limited to one working group? I think you're muted.
No. It's not limited. It's not limited to one working group. Sure.
Okay, so
sure.
someone can be.
No. But I think there's an organizational question in the next few years for LISA Consortium to sort out how you organize the interaction between the different working groups.
Okay, so again, I remind the audience, we have maybe 3 minutes for further questions. If you have any, you can post them here. So in the Zoom or on Slack. So there's another question. 1 second. Okay. So another question is that what do you find the most exciting prospect for fundamental physics with LISA?
Well, I think you mentioned it. The most exciting prospect, yeah, of course, that would be getting some signature of quantum gravity. Sure.
And do you think that will come more from the black hole side or the cosmology side?
That is a very good question. Very naively, at first sight or independently from any LISA considerations, I would have thought that cosmology would provide us with the best bet. You cannot deny the fact that in cosmology, we're inside the horizon of some singularity, whereas in the case of black holes, we're outside. My feeling is that this is ultimately going to be the key fact that yeah. Now, cosmology is an interesting in two ways. You have, of course, the inflationary fluctuations. Also there, by the way, we are reaching in the next decade or so an extremely interesting era at which the level of tensor fluctuations that will be possible to measure is reaching into a whole zoo of models, which are sort of small scale field models, which are theoretically very interesting. So connecting that kind of dynamics to the LISA frequency band is another very interesting cross correlation when you're asking about quantum gravity, I think. Yes, the LISA band would grow up more sort of the reheating era after inflation.
Okay, it's quite interesting. Yes, cannot wait myself for the results that will come maybe in 20 years.
Right.
Very well. Okay, thank you very much. Let's thank our speaker.